Hello everyone, welcome to this video. Today we're going to build a temperature alarm circuit that alerts us when the temperature gets too high. In this circuit, we'll be using a temperature sensor to measure the surrounding temperature, an op-amp comparator to process that information, and an alarm output that activates when the temperature goes beyond a set threshold. I'll walk you through each of these components step by step so you can see how they work together. By the end of this video, you'll have a solid understanding of how to create your own temperature alarm circuit and why each part is essential. Let's get started. First, we'll go over the objectives of our temperature alarm circuit. After explaining the circuit design, I'll show you a screenshot of the simulation setup so you can see the components we're using and how they're connected. Next, I'll run the simulation in real time. You'll get to see how the circuit behaves as the temperature changes and how the alarm triggers when it crosses the threshold. Finally, we'll wrap up with a conclusion where I'll summarize what we've learned, discuss some practical applications, and cover any challenges or improvements for this design. All right, let's jump right into it and start by looking at the objectives for our temperature alarm circuit. The objective here is to design a circuit that will sound an alarm whenever the temperature exceeds a set threshold, using a temperature sensor, an op-amp comparator, and an alarm output. Let's talk about comparators. A comparator is a specialized op-amp used to compare two voltages and output a digital signal that indicates which voltage is higher. Unlike regular op-amps, comparators lack a feedback network, allowing them to switch fully between positive and negative supply voltages. The threshold level is a reference voltage. When the input signal crosses this threshold, the output changes state, triggering a response. This makes comparators ideal for interfacing analog signals with digital circuits, enabling actions like switching or triggering based on specific voltage levels. Let us have a look at these two screenshots and see how the circuit behaves at 20% and 80% potentiometer input respectively. In case 1, when the input is 20%, which is less than potentiometer resistance, the circuit behaves as a closed circuit, whereas in case of 80% input given to potentiometer, the circuit behaves as open circuit as the input given is greater than potentiometer resistance. All right, now let's dive into the simulation to see our temperature alarm circuit in action. Here on the screen, you'll see a setup of the key components: the temperature sensor, the op-amp comparator, and the potentiometer. As we can see, the potentiometer is connected on this side. It is connected to the second pin of IC. This is the condition we created. This will work as input for complete CKE. We can adjust the potentiometer 0 to 100%. When on initial stages, such as from 0 to 25%, it is less than resistance in potentiometer, therefore the input flow and make it the closed CKE. Once the input to pot is more than its resistance, then it will stop the input flow, and the CKT will be open and will prevent the comp from burning. In summary, this temperature alarm circuit monitors heat levels and triggers an alert when the temperature exceeds a set threshold. With a temperature sensor feeding a signal to an op-amp comparator, the circuit activates an alarm to prevent overheating. It's a simple, effective solution for real-time temperature monitoring and safety.